like any other, dawn breaks and the sun climbs up into the eastern sky. But as its rays illuminate the world, no one senses that a strange transformation is about to begin. Gradually, a slight indentation appears in the great round disk of the sun. Minute by minute it grows, until after an hour, more than half the sun has disappeared. Now the day has become noticeably less bright, and shadows are getting sharper. As the sun narrows to a slender crescent, birds become agitated, confused by what seems like night arriving far too soon. Then, darkness descends, and up above, there's a strange, almost magical spectacle. In place of the sun, it looks like a perfectly round black hole has been punched in the sky. All around it, there's a ghostly white aura. The world is captivated by the ethereal beauty of a total eclipse of the sun.
We can only imagine how our prehistoric ancestors might have reacted to this incredible natural phenomenon, especially if it came upon them without warning. To them, a total eclipse might have seemed like the end of the world, or perhaps a sign from the gods.
Yet, as impressive as an eclipse can be, even more impressive is the fact that ancient people came to understand what causes them, and even how to predict them. The key is realizing that eclipses involve both the sun and the moon. A solar eclipse occurs when the moon passes in front of the sun, casting its shadow on Earth's surface. And when the moon moves to the opposite side of its orbit, so that it travels through Earth's shadow, the result is a lunar eclipse. But knowing exactly when an eclipse will take place is a bit more challenging. Although the moon circles around Earth once a month, eclipses are far less common. This is because a slight tilt in the moon's orbit means that most of the time, the shadows cast by the moon and the Earth don't line up in quite the right way. In any given year, only 4 or 5 eclipses are possible, usually in pairs, one lunar and one solar. Some of these eclipses are partial, which means that only part of the sun is blocked, or only part of the moon is shadowed. If not expected, such eclipses can easily pass unnoticed. Other eclipses happen when the weather is overcast, or they may appear in remote corners of the world, such as the high Arctic or Antarctica, where few people are watching. When all of these variables are factored in, it means very few people see more than a handful of eclipses over the course of a lifetime. Of these, most will be lunar eclipses, simply because when a lunar eclipse is underway, it can be seen anywhere that the moon is visible, roughly half the world at any given time. This means that our prehistoric ancestors almost certainly knew that eclipses can happen. But it wasn't until ancient skywatchers started keeping careful records over many generations that a longer-term pattern in eclipses began to emerge. That pattern is called the Saros cycle, and it was first discovered sometime after 750 BC by astronomers who lived in Mesopotamia, modern-day Iraq. They were among the first to notice that lunar eclipses with very similar characteristics seem to repeat every 6,585 days. That's just over 18 years, a period known as one Saros. Solar eclipses follow this pattern too, but it was harder for ancient people to detect this because solar eclipses in the same 18-year series happen in different parts of the world. Here, for example, is a spectacular image of a total eclipse of the sun observed in Mexico in July 1991. The next eclipse in this series happened right on schedule 18 years later in July 2009. But it was seen in China. It takes 3 Saros, about 54 years, for a similar solar eclipse to appear in roughly the same part of the world. Nevertheless, it's recorded that by around 585 BC, the Greek astronomer Thales successfully predicted a solar eclipse. Today, such ancient records can serve a scientific purpose. That's because astronomers can compare where eclipses were seen long ago to where the calculations say they should have been seen. The differences reveal slight changes in Earth's rotation over thousands of years. Today, scientists can predict exactly where and when eclipses will be seen, but that doesn't make them any less interesting. Instead, the mystery of eclipses has been replaced by anticipation, and for many, a deep desire to witness one of the most breathtaking sights in nature. Although the timing of an eclipse can be predicted to the second, eclipse watchers know that the end result can still be a surprise. For total eclipses of the moon, most of the surprise comes from Earth's atmosphere. As the lunar eclipse proceeds, the moon first slides into Earth's outer shadow, known as the penumbra, where only a portion of the sun's light is prevented from reaching the moon. This penumbral phase of the eclipse is barely noticeable. Later, the moon may hit the inner shadow, the umbra. At this point, a partial lunar eclipse begins, with some of the moon clearly in darkness. But even if the lunar eclipse is total and the moon enters the umbra completely, it doesn't disappear. Instead, a portion of the sun's light is refracted or bent as it passes through Earth's atmosphere and then redirected toward the moon. The light has a reddish tinge because it's red sunlight that can pass through the atmosphere most easily, just as it does during sunset. But how bright and how red the eclipsed moon appears depends strongly on how much sunlight gets through. When Earth's upper atmosphere is clear, the moon takes on a coppery color. When it's not so clear, the result is a dark crimson or even brownish lunar eclipse. This was proved to dramatic effect after the 1991 eruption of Mount Pinatubo in the Philippines. It was the largest volcanic eruption in over a century, and it lofted an estimated 20 tons of sulfur dioxide into the atmosphere. This produced a global haze layer that lasted for months. And when a total lunar eclipse occurred in December 1992, the moon was so dark it nearly disappeared.
Solar eclipses also vary in their appearance, but the reasons have more to do with observer location, and being in the right place at the right time usually takes some planning.
During a solar eclipse, the moon's shadow sweeps across Earth's surface. Any place where the shadow hits will at least see a partial eclipse of the sun. But to see a total solar eclipse, you need to be standing near the center of the moon's shadow, in a zone that's often only 100 kilometers or so wide, depending on latitude. This central part of the shadow traces a long, narrow track called the path of totality. On either side of the path, the solar eclipse is only partial. Inside it, viewers are treated to the full spectacle of a total solar eclipse. Getting onto the path of totality is well worth it, because it's only here that the most dramatic effects of a solar eclipse can be experienced. And the difference between a partial and a total eclipse of the sun is literally night and day. Even when it's only partly visible, the sun's blazing surface, known as the photosphere, easily outshines anything else in the sky. But once the photosphere is fully covered by the moon, the sun's wispy outer atmosphere appears. This is the corona. It's made up of ionized particles that have been blasted from the photosphere and heated to over 1 million degrees. The corona's feather-like structure is shaped by a powerful magnetic field which is generated inside the sun and extends far out into space. The field changes with an 11-year cycle that relates to the appearance of sunspots, darker, cooler regions on the sun's surface. When the sunspot cycle is at its maximum, the corona tends to be round and symmetrical. When there are few sunspots, it becomes long and spindly. It's this elongated version of the corona that may have led to the ancient Egyptian symbol of the winged sun. A total eclipse also offers a rare chance to study the long loops and filaments of plasma that are caught up in the sun's magnetic field. These are called solar prominences. In the middle of a total eclipse, when the sun is completely covered, prominences can often be seen glowing ruby red around the moon's dark perimeter. Together, all of these features add up to a remarkable sight that's different every time. And it's also fleeting. Because of the speed at which the moon's shadow passes across Earth's surface, a total eclipse generally only lasts a few minutes at most. In the final second, as sunlight creeps around the moon's receding edge, a sudden flare shines forth, creating the illusion of a diamond ring in the sky. For those watching, the diamond ring is like a parting gift from the solar eclipse, and a confirmation that something truly incredible has taken place. frigid plains of Mars, the sun shines pale and weak. But while the sun is far away, solar eclipses are not. Mars is orbited by two small moons, both of which can cross in front of the sun as seen from the Martian surface. No human has ever experienced this, but NASA's Curiosity rover has, and it's recorded them. This is Curiosity's view of a solar eclipse on Mars. Since the moons are small and irregular in shape, the sun is never blocked completely. Although interesting, the effects of a Martian solar eclipse are not especially dramatic. On Earth, it's a very different story. Here, eclipses have a history of making deep impressions wherever they appear. In some cases, they have changed the course of history. In March 1504, Christopher Columbus was beached in Jamaica when a book of astronomical tables alerted him to an approaching lunar eclipse. He used the eclipse to his advantage, impressing the local tribespeople with his apparent control of the event and persuading them to keep his crew supplied with food. 2 centuries later, in response to a challenge from U.S. authorities, a Shawnee spiritual leader named Tenskwatawa motivated his followers by forecasting the total solar eclipse of June 1806. Under the leadership of his brother Tecumseh, those followers would go on to play a key role in the War of 1812. Meanwhile, the Spanish astronomer José Joaquín de Ferrer traveled to the U.S. to observe the same 1806 eclipse. It's thought that he coined the term corona to describe what he saw around the eclipsed sun. Eclipse science got another boost 30 years later, when Francis Bailey, a retired stockbroker with no formal training in astronomy, traveled to Scotland to observe a solar eclipse. The eclipse was not total, because at that moment the moon was at a more distant point in its orbit than usual. That meant it was too small to cover the sun completely. So Bailey saw what is now called an annular eclipse, during which the exposed portion of the sun forms a ring or annulus around the moon. Bailey noticed that in some places the ring was so thin that the silhouettes of mountains on the moon broke through it, turning the ring into a string of beads. This effect has been called Bailey's beads ever since. Bailey's account of the phenomenon was so intriguing that by 1842 the next eclipse in Europe drew many more astronomers. Eclipse science was shifting into high gear. Over the following decades, several key discoveries were made during eclipses of the sun. But what may be the most scientifically significant eclipse of all time came in 1919. Only a few years earlier, Albert Einstein had published his theory of general relativity, which united space and time and predicted that gravity bends light. The theory offered a completely new way of thinking about the universe. The challenge was finding a way to test it. It was soon realized that during a total solar eclipse, it might be possible to see if the sun's gravity had an effect on the incoming light of background stars. Stars that would normally be too hard to observe while the sun is shining nearby. In the spring of 1919, an expedition led by British astronomer Arthur Eddington set out to put Einstein to the test. Watching from an island off the west coast of Africa, Eddington woke up on the day of the eclipse, May 29th, to overcast skies and heavy rain. Miraculously, just 18 minutes before totality, the clouds began to break up. By observing through clear patches, Eddington was able to make the crucial measurement. When Eddington presented his results back in England, he showed that the background stars had shifted just as predicted by Einstein's theory. At first, not all of his colleagues were convinced, but the news caused a global sensation, and overnight, Einstein became a household name. Today, the effect of gravity on light has become a powerful tool in cosmology. It can be used to turn vast clusters of galaxies into enormous natural lenses that can magnify our view of the more distant universe. But it all started with a solar eclipse.
100 years after Eddington, eclipse chasing is no longer just for scientists. It's practically a sport. Each time there's a total solar eclipse in an interesting part of the world, thousands travel just to be there, and the experience can be truly amazing.
And someday, that experience will no longer exist. Solar eclipses happen because the sun and the moon appear to be almost exactly the same size in our sky. The result is pure magic. But it's also a pure coincidence. As ancient eclipse records show us, the Earth's rotation is gradually slowing down over time. In response, the moon is gradually moving further away. Eventually, the moon will no longer appear large enough to cover the sun entirely. Astronomers estimate that the last total solar eclipse in Earth's history will happen about 600 million years from now. That still leaves us with many more chances to see one of the most incredible sights in the universe. But why wait? Eclipses are a natural wonder that seem tailor-made for humans to enjoy. And they're a reminder that even here on Earth, we live in a larger cosmic reality. A reality that seems unlimited in its capacity to enchant us.